So sound can also refract, which is essentially a fancy word for bend as well as it goes through a medium. And if you think about it, suppose we have a guy and he's putting out some wave crests. These wave crests kind of look like this, but we had regions where there's cold air and warm air. We know that cold air tends to be going relatively slow, and warm air is going to be going relatively fast. So you could convince yourself that down here, the wave's going to start to travel faster. And so it's going to be going faster and faster and faster, and slower and slower and slower. And what's going to happen is the wave is actually going to bend up. So maybe the dog is not going to wake up. If we had a region where we had warm air, again, warm air is going to be relatively fast. Over a region where it was relatively cold, or where it's going to be relatively slow, then you could convince yourself that if this is the wave crest and it's perfectly straight right here, that the top's going to start to move faster than the bottom is, and what's going to happen is the wave is going to bend down and, the dog wakes up. So, the book does say wind, but largely this is going to be driven by temperature. So let's just kind of think of some applications of this. Suppose we had a lake, and that lake was relatively warm, and it had some cool air that was on top of it. Then what's going to happen is we're going to have a temperature gradient, and if you're making some ruckus by a campfire, then what's going to happen is well, the light's going to tend, or the sound is going to tend to bend down, and what's going to happen is you're going to probably wake up some of your neighbors. Now, kind of the reality is whenever a sound hits a surface, it has it doesn't have the choice, but it can either reflect or it can refract, or it can do a little bit of both. Now, kind of an application of this is suppose we wanted to do an ultrasound. Again, that's going to be above 20,000 hertz. Then what's going to happen is we're going to send a wave down into a body, and it can penetrate that body, and we can actually study organs or babies and stuff like that. This is preferential to X-rays because X-rays tend to have higher energies associated with them with ultrasounds. And again, any surface, so there's the head of the baby, it's going to reflect, some of it's going to refract, some of it's going to go through, some's going to reflect off here. And since we know, the speed of these waves as they go through the body, then we can actually figure out, kind of where things are. Now, what if the object is moving? If you kind of remember, if we had a moving source, we could talk about that thing called the Doppler effect. And what you can actually see in some of the ultrasounds nowadays, you can actually see blood flow as it's going back and forth, and that's really, really, really cool stuff. Now, kind of other applications of this is dolphins and bats and stuff like that. What they do is they emit ultrasound waves, and what that allows them to do is to locate objects in their environment. So as this guy puts out an ultrasound wave, then what's going to happen is well, it's going to bend, but it's also going to get reflected back, and he's going to know, hey, there's a dolphin right there. And the same is true for bats. Again, this is not necessarily sounds that we can hear. We can hear some of them, but not all of them. Now, I do want to talk about the energy of waves. And energy of waves is going to be related to amplitude, but it's also going to be related to frequency. So suppose, I were to go ahead and take your leg and tie a rope to it. Then I could shake that rope any number of ways. I could shake that rope with a relatively low frequency, so back and forth, back and forth. And the lower frequency waves are not going to have as much energy. If I really want to wake you up, then I want to shake it, shake it, shake it, shake it, so you can kind of see much higher frequency. So the energy of the waves is actually going to be related to their frequency. And technically it's the frequency squared, but that's a bit beyond where we want to go in Physics 102. Okay, now I want to kind of change gears a little bit and talk about resonance, and it turns out that you can force something to vibrate. And what I mean by that is suppose we had, a factory floor, and you had some heavy machinery. If you were to drive that at just the right frequency, then that factory floor is going to be set into motion by some heavy machinery that was at just the right frequency. Now, it turns out that everything has its own natural frequency associated with it. And what it's going to depend on is how elastic an object is. It's going to depend on the mass as well as the shape if we're talking about a drum. And it's going to be related to how much tension an object has. And even if we were to talk about guitar strings, if I had a guitar string kind of like this, the tension is going to affect the frequency. How elastic the material was is going to affect the frequency as well as the mass of it. If this thing had lots of tension, then it's going to have a large frequency. So as the tension goes up, the frequency is also going to go up. Now, the mass of an object, we know that mass kind of means sluggishness. So if I had a guitar string where it had lots of mass on there, it turns out that the frequency would go down. So as the mass goes up, the frequency goes down. So these guys are inversely proportional, these guys are proportional. What we then try to do is we try to pluck an object at its natural frequency, and what it tends to do is it tends to resonate. And probably not surprisingly, we call this resonance. And that's just when the force vibration on an object matches its own natural frequency. So if you picture, like one of those swinging bridges that you crossed as a kid and you can make it swing at just the right frequency, essentially what you were doing is you were driving it at just the right frequency. I'm going to talk about radio stations especially in a couple of things, but essentially when you tune your radio to 102.5, you're tuning it to the carrier frequency of that radio. And we could also have something like troops marching across a bridge, but actually I have a slightly better example. There was a bridge in Tacoma, Washington, and that bridge was driven by the wind at just the right frequency. And you can kind of see here the bridge is bending and bending and bending. And I highly recommend you just watch it on YouTube. I'm not going to force you to watch through it. But at some point, the bridge actually fell down into the water. So check out that link or check it out on YouTube. Really just a quick, cool example of resonance where the wind was driving the bridge at just the right frequency. Now, I do want to talk really quickly about natural frequencies. So suppose I had a sound, a trumpet, a voice, or something like that, and it's putting out some mechanical waves. Well, those sound waves can get picked up by a membrane, like a microphone. Then we actually turn that into an electronic signal. Then what we do is we go ahead and mix that electronic signal in with a carrier frequency using something called a modulator. Now, that carrier frequency is going to be whatever, the frequency that the wave, or whatever frequency that is inherent to that radio. So here we've taken this carrier frequency and we've modulated it with the electronic frequency. Now, it turns out that there are two ways we could actually do that. We could modulate it in the amplitude, or we could modulate it with the frequency. And I just want to talk about the difference between the two of those in the next couple of slides. Now, when we talk about AM radio, we're talking about amplitude modulation. And what we have is we have this carrier frequency. And again, that's a property of, whatever radio station we have. You can kind of see that we've modulated the signal right here on the amplitude. Now, there's pros and cons to doing it this way. It turns out you can get more power, but it tends to sound a little bit more grainy. So all the information is included in the amplitude of the signal. Now, we also have FM radio, and FM is frequency modulated radio. And in that case right there, so we have the carrier frequency, but then we kind of dither very slightly around that carrier frequency. And all the information is actually encoded in the dithering of the frequency around that carrier frequency. And again, there's pros and cons to this one as well. It turns out that it's better quality sound, but maybe not as strong of a signal. Then kind of what happens is, well, we have our antenna and we set our radio to either AM or we set our radio to FM. And then what it has is you tune it to whatever station you're interested in, and then it, probably not surprisingly, demodulates it. It picks out the carrier frequency, that's what you turn the knob to, then it picks out the signal, and then it spits it out to the speakers, and then we have sound which can then once again reach your ears. Now, the last concept I want to talk about is something I alluded to in Chapter 19, and that is interference. And I said that if we have two sound waves that live at the same place in the same time, then they can superimpose. They can both live there, and they can either reinforce each other, or they can cancel each other out. And this would be what we call constructive interference, and this would be what we call destructive interference. And again, you can kind of see that these two guys are going to reinforce, so it's going to have a big peak right here and a big trough right here. These guys, this one pulls up and that one pulls down, so they can reinforce or they can cancel each other out. Now, this is a property of all waves, not just sound waves, but any mechanical wave, as well as light waves as well. Now, what does this look like for different waves? Well, we've talked about transverse waves, where the medium is moving up and down and the wave moves side to side. Pretty straightforward. This plus this is equal to this. It's a little bit harder to picture with longitudinal waves, but longitudinal waves, here we have some pressure waves, and here we have, here we have all of our air molecules bunched up together, and the rarefications are in between. So this plus this, as long as everything is in phase and everything like that, then what we're going to get is we're going to get more stuff packed in here, right here, and we're going to have even less stuff packed right down here. Yeah, and these two are going to be examples of what we would call the constructive interference, where it has reinforced, but we can also have the opposite. We could have this wave plus this wave. They're totally out of phase, out of step, and so where they are superimposed, they're actually going to have destructive interference. For sound waves, you can kind of see where this guy is bunched together. This guy has a rarefication, and so when these two guys add together, then we're going to get destructive as well. We're not going to have any air movement whatsoever. Now, real-life applications of this is going to be noise-canceling headphones. If we have something that's really noisy, like a jackhammer or an airplane engine or something like that, then what we can have is we can have a microphone on the outside of our earbuds. And what that thing is going to do is it's going to sense kind of what's coming in, and then it's going to feed in something that is the exact opposite. So you can kind of see a big peak right here, big negative peak right here, negative peak, big peak, negative peak. And what's going to go into your ear is going to essentially be white noise or very, very, very little. Now, this type of noise-canceling headset is actually really good for your ear, because if you wanted to put some music into your ear, then you don't have to overcome this big loud sound. So noise-canceling headphones are actually much, much, much better for your ear than just cranking it up. Now, the last thing I want to talk about is what happens if we have two sounds and they're not at the same frequency, or they're not always in phase or not always out of phase. Well, what we're actually going to hear is we're actually going to hear something called beats. And what we're going to hear is we're going to hear just the loudness going up and down. So maybe kind of something that sounds like a wah, wah, wah. Now, suppose we had, tuning fork number 1 and tuning fork number 2. You can kind of see that this guy has a long wavelength. This guy has a short wavelength. And when they line up right here, then we're going to have constructive interference. Where they line up and they're out of phase, then we're going to have constructive interference. We're going to have destructive interference. So kind of interesting that if this guy was at 100 hertz and this guy right here was at 150 hertz, then what we're going to hear is we're going to hear the 100 hertz. We're going to hear the 150 hertz. We're also going to hear a beat frequency that's kind of the difference between them. So it would be 150 minus 100, and we would also hear a beat frequency of around 50 hertz. So we would hear kind of a wah, wah, wah type of thing. Now, kind of some applications of beats is a piano tuner. What they're going to do is they're going to have a tuning fork, and that tuning fork is going to say, this should be in C sharp, and it should be 256 hertz or something like that. So what they'll do is they'll play the tuning fork next to the unknown piano, and the piano tuner will listen for beats until it matches the note that he or she is trying to get at. Essentially, all they're trying to do is they're trying to match the same exact frequency, so that way the beats kind of go away. Musicians, they're really, really good at doing this thing. They listen for beats between instruments and kind of tune them kind of on the fly as things heat up and stuff like that. I am not very musical inclined, so I'm not the best person to listen for beats. So here I have an example where I have 250 hertz and 257 hertz, and you can kind of hear a beat frequency, and I'm just going to dither with the frequency, and you can hear it change.